Hi guys, we're moving on with actually doing something now with these linearized equations of motion that we've got. So we derived our equations of motion in the form x dot is equal to the system matrix multiplied by our state vector plus the control matrix multiplied by our control vector. So we've derived this for both the longitudinal equations of motion and the lateral directional. So the x vector for our longitudinal equations of motion is perturbational u, perturbational w, q, and theta. So this is for, let's put this down here, let's say longitudinal. And then for the lateral directional, our x vector is v, p, r, phi, and psi. And then we develop different matrices for A and B. And now we're actually going to do some stuff with them. So I'm going to go through a little bit of theory today, but we're really just going through an example. And we've gone as far as we can at the moment without you guys just doing the work here. You need to go through this example. So included in the website, let me just switch over. I have gone through a full example of taking some data for a Boeing 747 and then getting the non-dimensional stability derivatives and doing the real nasty task of turning them into the dimensional stability derivatives, putting them into the longitudinal and the lateral directional matrix or matrices, and then doing a quick using the inbuilt control system functions to look at the behavior of this system in response to a control impulse. So this is a control impulse in elevator. So this is the longitudinal equations of motion. We see forward speed, heave velocity, pitch rate, and pitch attitude. And I want you guys to go through and see where these things come from. And then we do the same for lateral directional. So that's looking at the angle of attack there. We then do the same for the lateral directional. But there are two controls for the lateral directional. So the first one is a response to a unit rudder input. And then we're looking at side slip, roll, yaw, and roll attitude. And then we do the same for a unit aileron input. Okay, so I'm going to go through a little bit of the theory that we need now to understand how to build those matrices back together. Probably the most difficult part of this is getting the getting the coefficients or the stability derivatives in coefficient non-dimensional form into the form of into the sort of whatever dimensional form we're looking for, be it in SI units or be it in US customary units. So in fact, let me just put this back up. I'm also aware that with this new haircut, I look like a little boy right now, but I was better than a slightly lazy looking hippie teaching me flight mechanics. So I'm just going back over here now. So where I've taken these data from, I was originally looking at data in the Schmidt textbook. I'm not entirely comfortable with the relationship between some of the dimensional and non-dimensional stability derivatives in that book. So I found a whole set of other data. We are now looking at it here, so presented in this site, which if you click on it, site CITE takes you to this one, which is a report from 1972, Aircraft Handling Qualities Data, and it has an accompanying site SITE website. There we go here, and you'll find that it's a 352-page document comprising stability derivatives for different aircraft: NT-33A, F104 Phantom, F4C, X-15, and importantly, we've got the one here. We're looking at, well, there's a Corvair aircraft, there's a Jetstar, but the Boeing 747. So I'm looking at that one here, but that would be interesting to look at the XP-70A as well. So have a look at these different aircraft. I'm going to go through the 747. You guys are going to be tasked with doing a similar job for different aircraft. So I'm not going to go into detail on this document. I'm just going to pull bits out of it and do a demonstration of how we take those non-dimensional stability derivatives and turn them into dimensional ones that actually mean something for us. So let me pull some of these in. So the matrix that we're trying to actually produce, I'm going to go through the longitudinal matrix. So we're looking at this one here. I'm going to make this larger in a second. And these are the data we're looking at. So I've taken, okay, we need to be able to produce these things. XU, XW, There is no XQ for this aircraft. If we were given a CXQ or a CDQ term, we'd have to include that, but we haven't. And again, there's all parts of this included in the accompanying notes. So we need to find all of these derivatives based upon these non-dimensional ones that we've been given. So we've got the non-dimensional stability derivatives. We need to work out how we convert between them. Now it's not always entirely clear how these relate, but if you look at them and use some of the tables that are included in the accompanying notes, then all will become clear, or slightly clearer, I would hope. So let me go through this. We're going to work on this one here, and I'm going to go through term by term how we get them out. So let's go through XW first. This page is going to get very messy as I go around it, but let's go over here. Sorry, not XW, XU is what I meant. So let's go all the way over here. So XU, how do we work out what this term is? Well, we know that it's 1 on M, and then it's the partial derivative of the longitudinal force in stability axes with perturbation or forward speed. Doesn't really help us though at the moment. So we're going to go and have a look in the accompanying notes at the non-dimensional equations of motion. And then we're going to go down and see what else we can find. So this is, if we wanted to use these stability derivatives on their own, we'd use them in this format. But I don't find this format particularly useful, because what we get out in terms of our states, they're sort of non-dimensional velocities. So they don't make a tremendous amount of sense in terms of inferring real things about the aircraft. So, well, I can see it written right here. I've got XU, and I talk about what XU is here, because I use this as an example of how difficult it is to really go through one by one. Not so much difficult, but it's an involved process, getting the non-dimensional derivatives into this form. So the easiest way to do is to look at these tables that are included here, which is entitled Converting from Non-Dimensional to Dimensional Stability Derivatives. And then I've got XU here, and we can see this term here. So it's, I don't know how well you can see that, but it's XU is equal to dynamic pressure multiplied by the wing area divided by the mass of the aircraft divided by the trim forward speed, and then it's open brackets 2x naught plus 2cxu. Okay, so I do go through this and I sort of say where this comes from further up here. So if you go through here, you'll understand where it comes from, but we can just use this table to see where different things come from. So let me copy that one down. So XU, let's move that over. Let's move this arrow so it's not all over my face. So XU is QS on MU naught 2CX naught plus CXU. So we need to look at our dimensional derivatives and find out a CX naught and a 2CXU. So let's have a look. Let's go to our derivatives. Well, we've already hit a problem because we don't see anything involving CX down here. We've got them in terms of lift and drag. So let's do a quick think about how things work in sort of our stability axes. So if we have our aircraft here in stability axes, then we've got force coming along here, so the velocity coming along to the aircraft. This means that our stability axes are along here. So I have my X force and my Z force, and then my lift and drag sorry, that's the wrong one. Lift and drag are opposing this axis. So CX is equal to minus CD. So we were looking for CX naught, so that now becomes minus CD naught. So this is not a rate of change, this is just the trim value of drag. Okay, so the naught is there, which means we can just take the CD value from this table. This is from the paper. This is our CD naught. And that's equal to minus CX naught. And then we've got this up here. got this term here, CXU. So we would want to look for either a CDU term, or sometimes what we'll see CDU could be written as CDU is equal to the Mach number multiplied by the rate of change of drag with Mach number. Okay, so you guys can go through and do the chain rule partial derivative to show that's true. So we want to see if this table has either a CDM, which is the rate of change of the drag coefficient with Mach number, or a CDU term. And if it doesn't have either of those, we can just assume they're equal to 0. So let's have a look for CDs. I've got CD there. I've got C, so that hasn't got a Mach number. CD alpha, no. I've got CD and CD alpha. So we're going to assume that CDM and CDU are both equal to 0 for our case. So we've got this up here now. Let me just move this a little bit further up so I've got more space to work on the page. Okay, so we've now got this expression here. So we know that it was 0.102. So our CX0 is equal to minus CD0, which is equal to minus 0.102. Is that right? I'm so bad at remembering numbers. Yeah, 0.102 is this term here. So we now need, since this one is equal to 0, we need to know everything on this side. So we need to know dynamic pressure, wing area, mass of the aircraft, and the trim forward speed. So we can get those from the document itself. You can find out all of those, and then I'm just going to copy them down onto this page. So we are told it's at sea level. So sea level density and everything else is given in US customary units. So I best quote this in US customary. 0.0765 pounds per cubic feet. And then we've got the wing area, and I think I know this one off by heart, is 5,500 square feet. We've got the wingspan. In fact, we don't need the wingspan here, so I don't need that. The mass of the aircraft is in 564,000 pounds. And the trim flight speed is, where is it? I've got it written down somewhere. I think it's 165 knots, but I don't want to get that wrong. It's 165 knots. It's 165 knots true airspeed, and we can convert that to feet per second for US customary units. So that becomes 165 multiplied by 1.68781. Not a number I'd remember. I'd probably convert it to meters per second, which is multiplying by 0.5144444, and then convert it to feet per second by dividing by 0.3048, which actually is just what this number will be now. So this gives us a U-naught of 278.49 feet per second. So we can put all of these together to get our XU term here. So XU is equal to a half multiplied by the density, 0.0765, multiplied by 278.49 squared, multiplied by 5,500, divided by the mass, so 564 times 10 to the 3, multiplied by the forward speed again. So that's 278.49 multiplied by 2 CXU, but remember it's minus CXU, so this whole thing is then minus, multiplied by 2, multiplied by 0.102. So let's put all of this nonsense into my calculator. 0.5 times 565 times 278.49 squared multiplied by 5500. 564 times 10 to the 3. No, that's not the right number I put in. 564 times 10 to the 3 multiplied by 278.49 multiplied by 2 multiplied by 0.102. There we go. And I know that number's correct because I've done this nothing but this problem for the last couple of hours. I'm deliberately not going to put any units next to this, okay? I should be putting units next to them, but I'm not going to at the moment, and we're going to have a think about why. So we did this taking from non-dimensional stability derivatives and then putting them into dimensional normalized stability derivatives, remembering that's xu is equal to 1 over m dx by du by using US customary units. Like I say, one of the reasons why I'm a little late with this lecture is because I insist on giving you guys examples in US customary units, even though I hate doing it and I'm really bad at doing it because I only ever work in SI. If I have to present anything in US customary, or if I had to during my career, I converted to SI at the beginning, converted to US customary at the end, and that's what I advise you guys to do in real life. But I feel I had to go through a full example, and the issue with this is that in the document they present some things in slugs and some things in pounds. So I was out by a factor of 32.174. That's my rant about units over. But now we're here, let's go through these stability derivatives. So this is the value of xu, which is the rate of change of the perturbational x force with perturbational forward speed when we've used US customary units. So let's see what it would be when we use SI units. Okay, so using SI units, rho is equal to 1.225 kilograms per cubic meter. S is equal to 5500 multiplied by 0.3048 square meters. These are just numbers that I remember now. The mass is equal to, I don't remember this one off the top of my head. Mass is equal to, it's about divide by 2.2, but it's not quite that. So it's 564 times 10 to the 3 multiplied by 0.453592. And then U naught is going to be equal to 165 multiplied by 0.514444. So if we do all of these together, we'll get xu is equal to minus 0.5 times 1.225 multiplied by 165 times 0.51444 ... squared multiplied by 5500 multiplied by 0.3048 squared all over 564 times 10 to the 3 multiplied by 0.45 and the rest of that number in there multiplied by the flight speed, which is 165 multiplied by 0.51444. I'm not writing these numbers out on purpose. Multiplied by 2 multiplied by 0.102. So this would be if we use SI units. So I encourage you to go through and do that calculation. If you do, you'll find out we get the exact same answer out, minus 0.0212, which is confusing because these are dimensional derivatives, and we've taken non-dimensional terms and we've multiplied them by the things that correspond to the measurement system or the unit system we're working in. But we've ended up with the same answer, which is slightly counterintuitive. So this is where we need to think about the units of these derivatives. So let's have a look at xu. Xu is equal to 1 over m multiplied by dx on du. So that's going to be 1 over kilograms multiplied by newtons on meters per second. Let's go up here. Well, that's equal to 1 over kilograms multiplied by kilograms meters per second squared divided by meters per second. So the kilograms cancel, these cancel, and those cancel to give us seconds to the -1. So the units of both of these are just seconds to the -1. And that's going to be the same for any of these derivatives. That is a force, so that's going to be x, y, or z, with respect to a perturbational velocity. So we'd have things like xu, xw, and I've done that the wrong way around. It should be x. We don't have xv, we've only got xw there, that's y. We would have yv, and we'd have zu and, for example, zw here. I've not put the other ones in because they would represent cross couplings between symmetric and asymmetric modes. But all of these are all going to have the same units of just seconds to the -1. Now, thankfully, but there's no weird sort of metric second we use, and there's no sort of US customary system where we got 4,028 seconds to a minute or anything. So those are both the same for this, but it's not going to be the same with all of these. So with other derivatives, we will see different numbers come out, whether we use US customary or whether we use SI units. And it depends on which sort of derivatives we're looking at. A lot of the ones involving moments and a lot of the ones involving angular rates will give us different numbers when we get them out of the actual different numbers when we're using either SI or US customary. But I just wanted to make that point here that we can get different numbers out of these depending which measurement system we're looking at. XW is easy to get on here as well. Let's go through. So we've got XU, it's minus 0.0212. Let's get XW out now. Okay, XW, let's go down here. XW, we know it doesn't matter whether we now use imperial or SI for this. I'm going to keep using imperial because that's all US customary, because that's what I started to do this example with. So if we want to look at how we get this from non-dimensional to dimensional, we go back to the notes. We can go, if you really want to see all of these and how they all work, you could just go to the worked example. I encourage you not to do it this way. I encourage you to maybe look at the worked example and then go back and forth into the notes and see how I've got different terms out. But here we could see that XW, I'm going to have CL minus CDA here. Let's go and see where this comes from. So we'll go to the non-dimensional equations of motion. And then we'll look down at the conversion between. So conversion from non-dimensional to dimensional stability derivatives. So I've got XW. Okay, so XW here is defined as Q. I'm not going to write the infinity. So dynamic pressure, wing area on mu naught. I wish I'd written that number down. Multiplied by Cx alpha. So Cx alpha is a new one. Oh, let's get the board up behind me. So Cx alpha. Not quite certain what Cx alpha is in this sense. So we need to go and have a look and see if there's anything in the notes that will help us for this. So I want you guys to have a look and understand anything involving an alpha term here is going to be slightly different. So we can see that Cx alpha, and I go through and give you the reasoning for why this is done, but Cx alpha is equal to CL naught minus dCd by d alpha, which is CD alpha in this case. Okay, and that comes, so that's just, yeah, that's that one there. Okay, so that's this expression here. I just switched it round here. Okay, so that's CL naught minus CD alpha. So we can then look again back at the, so we're looking for CL naught and CD alpha. Over here we've got, okay, this is our CL naught, and this is our CD alpha. So we've got both of those, 1.11 and 0.66. bit of caution to note in this as well. These are listed as being, in this document, as listed as being per radian. I don't think that can be true. These are non-dimensional rates in here. So these are, by definition, unitless. And to convert them back to dimensional rates, we do have to convert the rates from being non-dimensional as well. So just where there's a rate term, P, Q, or R, ignore the fact that it says radians here, because I don't think that's correct. But we're going back to this term over here. We've now got the numbers to put in here. So I'm going to just look in my code. I'm going to get out what this whole term is here rather than write it out in one. So let's Q times S divided by M multiplied by U, that's 0.10387777. That's probably more precision than I need, but I can do that in intermediate steps. And then I've got 1.11 minus 0.66. Let's do all this. I'm just going to do this on my Jupyter notebook. Okay, so I get 0.047745. Okay, that's my XW term. And again, this is seconds to the -1. So this one wouldn't change no matter what measurement system I'm using, whether I'm using the US customary or whether I'm using the SI correct system to use. Okay, I'm not going to, let me just check, I don't think they're too difficult to get. No, let's do these as well. Okay, so this one's easy to get. We are not told theta naught in this, but we assume it's 0 in this case. So we just end up with G, and we end up with G here, and again, if sine 0 is 0, this ends up as a 0 term here. So this becomes minus G. This becomes 0 for our case here. If we're not told theta, we can just assume it's 0. Let's do ZU now. So ZU, again, remember, is 1 over M dz on du. And again, just to confirm how we get this, we can go look at the notes. We can see the equation that's going to help us remind to go through this. So ZU is Q S M U naught CZ naught plus CZU. Again, we can remember all of the same things about, let me get my blackboard up here. So let's remember that CZ is equal to minus CL. So what we're looking for in the stability derivatives, we want to see if there's a CL0 term, which is just going to be our CL term, the trim lift coefficient. And then we want to see if there's a CL with respect to forward speed, rate of change of lift with forward speed, which you probably won't see, or if there's a CLM, a rate of change of lift coefficient with Mach number. If we have either of those, we can include them here. So what we would include this is Mach number multiplied by CLM. So let's go over here. Well, we've got CL, which is 1.11, which we know already. And then the other term that we need is no, I've made a mistake there. CZU, it's CDM is one I want, not. No, I'm being stupid. Sorry, it is CLM. I'm being stupid. Disregard my confusion there. Okay, so I want CLM. Which do I have? I do. I've got it here. It's minus 0.81. We're not told the Mach number, but we can work it out. So CL, we already knew from before, was 1.11. And CLM was minus 0.81, I think. Yes, minus 0.81. So we now just need to know the Mach number of our aircraft. So let's just put these in. We've got ZU is equal to QS on MU, and I had that number a minute ago. That number was, where did I write that down? Oh, here we go, it's this number right here. Okay, so this number was the QS on MU is this number here. So it's 0.10387777 multiplied by, just move this over. Now we need to put CL naught, which is our 1.11, but it's going to be a minus 1.11 because CZ is equal to minus CL, plus CZU, which is going to be this term here. So it's going to be minus this number, which means we plus this number, plus 0.81 multiplied by the Mach number, which we have to work out. I'm not going to go through how we calculate the Mach number for different aircraft. We know we've got the sea level sonic velocity. It's going to be 340 meters per second, or I could ask you guys to sort of work it out. But the Mach number for this aircraft is 0.247 for the condition that it's at. So let's work this out. Again, I'm just going to do this on there's a mistake in here. It's this one here. If we go back to the accompanying notes, this is where this can be a real ball ache to do if you're doing it live. If we look where this comes from, this expression is ZU. Okay, ZU is equal to this bit down here. This is this expression in here. There should be a 2 here. So it's 2 multiplied by CZU, which means that 2 should be multiplied by this term here. So let's just put this multiplied by 2. This is a very messy workbook now. So then if I thought that number I was getting didn't look right, so there we go. My ZU is minus 0.2098. Okay. So that one's done. ZW, I'm not going to go through calculating because I actually, do I give that down, ZW? Yeah, I do, because I give CZW, which is minus CD naught minus CL. So go through the accompanying notes, check out where you get this CZ naught here. Sorry, not CZ naught, CZ alpha. And then if we're looking for ZW, you get this expression here. And then you'll be able to calculate what this one here is. And again, in the accompanying notes, I go through a full worked example, which actually you can go through, and if you can follow this through, then you guys can go through and say, okay, well, using this exact example, I can see how all of these are calculated, and I get a ZW term of minus 0.6027 here. So you can see how all of these are calculated, see how they transit through. Oh, that's my playing around has been included here just to check. So look at the, this is where I was playing around earlier to look at whether this term changes with using 2 different systems of measurement, using SI or US customary, and I uploaded those accidentally. Let's just go and have a look at the last couple of terms in this matrix. So those are pretty easy to get. The ones that are going to be slightly more difficult are remembering that these MU terms, etc., where they come from. So the MU star term, you've just got to remember that MU star, if by definition is equal to mu plus mw dot multiplied by zu. So by this point you'd already have this zu term. We can work out mw dot by, again, we go to the company notes, we just see where things come from. Let's go find mw dots. So we'll go to non-dimensional equations of motion. We've got mw dot is here. It says that mw dot is equal to q multiplied by the dynamic pressure multiplied by the wing area multiplied by the mean aerodynamic chord squared divided by 2 times the mass multiplied by the flight speed squared multiplied by cm alpha dot. Okay, so cm alpha is just a term that we are given in here. So let's bring this up. So that's a pretty easy conversion to do. And again, if we go into the worked example, just pulling the notes out of the way, we can see that how all of these are converted. We get mw is just that external expression multiplied by cm alpha, and then we've got down here all of those starred terms are calculated here. So it's mu plus mdw multiplied by zu here. Okay, so what I want you guys to go through is understand how this matrix is constructed. Getting this matrix, because this one here, the system matrix, tells us everything about how the aircraft wants to respond. So we can build this matrix. We can do a very similar thing with the lateral directional one as well. We can build the lateral directional matrix and we get this out for it. Now, it's quite a bit of work to get here, but I want you guys to go through and understand this example, because I'm going to ask you to pick other aircraft out of this PDF, choose the stability derivatives and get these out for them. Because then what we can do, there's actually a whole bunch of things that are just built into Python that we can import. You might have to install a package to do this, and if you need to install the control system toolbox, you click here, shows you how to install this toolbox here. Okay, but we can go back. This is very similar to the control system in MATLAB, sorry, the control system toolbox in MATLAB. And if you want to do this in MATLAB, be my guest if you want to be brought into MATLAB still. The way that we create these, I create a system here. So then I have to create my control matrix as well, which is my B matrix. Now we know that's just ZDE and MDE star here. Okay, that's from the equations of motion in concise form. I can work out what these two things are based upon the non-dimensional stability derivatives and put them in. I convert them from per radians to per degree, and just read through and see why I've done that. Okay, you should be able to follow the logic and see why I do that and why actually I'm using the radian function to do that. Okay, it's because I'm doing it from per radian to per degree. It's the same as turning degrees to radians. What we then do is we then create an object, which is the longitudinal state space form. I include my A matrix, my B matrix, an identity matrix the same size as the A matrix, and a zero matrix the same size as the C matrix. This is because, again, you'll remember this from control system theory. We've got the matrix, we've got the ODEs that describe our actual system, the A and the B matrix, and we could then have an output equation which would enable us to put different variables being output. Those would be our C and D expressions. If we don't have the C and D matrices, we've got to include an identity matrix that basically says we don't want to do anything with the output other than give out the output from our A and B matrix. I can then just say what I want to get out is I get my time, my perturbational U, W, and Q, and theta. I want to just see what the output is if I do an impulse. And there's only one control for this system here, which is the elevator. So we'll put a unit elevator deflection in. And I said here, go from 0 to 200 seconds. And I want you to do 10,000 steps, which is maybe a bit of overkill. But then what we get to plot is plot these different things. We're plotting perturbational forward speed, perturbational heave velocity, pitch rate, and pitch attitude. So we can zoom in on these and we can see, well, there's a perturbational forward speed, there's this long and slow oscillation. Heave velocity, which is related to angle of attack, we can see there's a big immediate excursion, and then there is again this sort of short-term, longer oscillation that's occurring. Pitch rate, again, there's this very fast, let's go over here. We see there's this immediate excursion, and then again this sort of slower response, and the same with pitch attitude. We sort of see both these behaviors being present in the first bit. We see this short-term response and then this long-term, longer behavior. And we're going to talk about these a lot in Module 5. These are two very, well, they are the two characteristic longitudinal modes of aircraft motion, the short period and the phugoid mode of the aircraft. And we're going to talk more about them. I encourage you to take this, make your own notebooks, just copy the code out, but understand what each line does. And in here, I also enable you to, if you want to take this page and run it, get your own copy, then you can do everything in SI units, and it will convert all of the aircraft data from imperial to SI units. I import my non-dimensional derivatives using dictionaries, which is maybe not what you're used to doing, but it enables me to put all of these terms in one go, and I could also then actually import these quite easily from an Excel spreadsheet in the future. And I then do something a little bit cheeky here, as I say, take all of these values in my dictionary and update the local namespace with what's in here. And that means that I can then, further down here, I can say XU is equal to all these things multiplied by CD. I haven't actually defined this variable CD anywhere. I define it as, instead in this dictionary. And then when I've said down here, update all of the local variables or the local namespace variables with what was in this dictionary, it means that all of these key value pairs are then available down here. So just try and get your head around what's going on here. So I do those for the longitudinal response, and then we do the same with the lateral response. I want you to read through this, understand where it comes from, try and repeat it, make sure you've got your own working notebook. And I then talk about how we could say, rather than just looking at those state variables, we could look at some non-state variables, such as angle of attack. And we see actually the angle of attack change is quite a bit smaller than the pitch attitude change. And I want you guys to think about why. Okay, so this sort of long-term perturbation is quite small compared to the long-term perturbation here, but the short-term perturbation is quite big. So we're going to think about that, and we're going to think about what that means for those two modes of motion. We then do the same thing with the lateral response. It's much of the same coding here. I then do a unit rudder inputs, and we see that the rudder largely causes a change in side slip, and then it slightly changes the roll attitude, which settles back. And then we see the roll rate and yaw rate both have these oscillatory responses. But we see the largest response is from the side slip, which is what we'd expect. And then down here we do the same with the unit aileron. Okay, these are all normalized scales, but we can see the largest response here is it's a large roll rate is affected, which is what the ailerons affect, and then it excites all of these other modes. And we'll discover there are actually three characteristic modes of motion we've got in here. We've got the Dutch roll mode, which is the only oscillatory thing we see, this sort of up and down, is because of something called the Dutch roll mode. We've also got the roll mode, which is what's causing the damping in this roll attitude, which we'll see. And then we've got the spiral mode. Spiral can be a mode that causes us to move off of an aircraft. Now, I'm probably certain that the spiral mode is probably stable for the 747, but I haven't gone through and looked at these data. And what we're going to discover is actually we can get all the information about these modes from the A matrix on each of these. So there is part of here, I think I maybe commented it out. Yeah, I did. So when I was going through and testing it, I got this method correct by doing both the doing both the US customary and the SI units. I was checking the eigenvalues of these matrices to check if they were correct or not, and that's why these lines are commented out, but I've left them in there because they sort of show you what I was doing when I was going through. So what I would like you guys to go through is this example in its entirety. Okay, make sure you know where each thing's coming from in here. You could be a sort of crappy undergraduate and do the sort of thing where you think, well, I can just follow this example and I could repeat this and just change the numbers. And you can do that if you want to, but you'll really struggle with understanding. I want you guys to understand this stuff, and I want you to be able to think, yeah, I understand where that derivative is and what it physically represents. XU, that is the rate of change of longitudinal force due to perturbation or forward velocity, otherwise known as speed damping. And so this is going to be affected by things like compressibility. So that will give me a CDM term that goes into that. So I want you guys to think in those terms and go through this example. And what I also want you guys to do is to get a copy of that document. Okay, get a copy of this this document, which is here. And if it loads up, that's from the NASA. Oh, it's here anyway, so we can go here. You can get a copy of this document because there's lots of other different aircraft in here, and I'm going to assume you have a copy of this for the weekend so I can get you guys to go through and do these examples. If there are questions on this, pop it on Slack. I want you guys to see, question how I'm doing different things and what we're ending up with. Because I'm going to assume you can get things into this state space form because we're going to be working with it from now on. We're going to be working with state space form for different aircraft to understand the aircraft response. So we're going to break down the longitudinal and the lateral directional modes into understanding what's in each of these modes of motion. So we're going to, we don't want to look at that one, we want to look at this one. We're going to see, for an aircraft, what can we actually tell about these modes of motion? Because we don't want to do a sort of impulse response and look at it every time. We want to see, by looking at the matrix itself, can we determine system stability? And we know we can, because you guys have done control system theory. We can look at the open loop response just based upon the A matrix itself, not involving that B matrix at all. So we're going to move ahead with that next week, but you guys have got to go through this example and you've got to understand it. And if you don't, you've got to get in touch with me. Okay? Appreciate you guys' patience with this week being a little bit, well, it was a day late out. Like I say, it's because I went through some data. I historically have not gone through the non-dimensional to dimensional stuff before, because not being from America, it's not what I was taught to do as an undergraduate. So, but I've started to do it more here. It's also very difficult to examine in that stuff because it's such a pain to do any assessment on. You could never do that in an examination, because those derivatives are so fiddly to work out. But now it's all open book in this brave new world we're in. I trust you guys to do it at home and to go through and work through it. So where I was getting to is why this took so long is because going through the textbook that I use for my previous examples, some of those data don't match up between dimensional and non-dimensional forms. So either something slightly funny is being done with the data, or it's maybe just a mistake in the book, but I didn't want to present it to you guys because I wasn't comfortable with those examples myself. But the data presented in the NASA report that I shared is good for us to work with, and because I've taken those data for, say, the Boeing 747 and compared it to what I know to be the phugoid period of this aircraft, and they all work. So get the data, go through it, and if you can go through this example, you'll be able to do your homework that's coming. So I look forward to seeing you all later this week, and I will be in touch soon. Take care, guys.